Greetings and salutations, everybody. This is Jacob. Okay, in order to solve this problem, we'll be making use of graph theory. Of course, you can stumble upon a solution by accident or use brute force. That's not how we'll be doing things on this channel. Every problem on this channel will be strictly mathematically modeled and solved within the frameworks of theory. Of course, the exception to this rule is lateral thinking puzzles, where no math is needed, of course. So what is graph theory, you ask? Good question. Graph theory is the area of mathematics that deals with graphs. When I say graphs, I don't mean an XY Cartesian graph, like the graph of an equation. A graph basically is an abstract model of a network. This network can be anything: a road network, a telephone network, relationships between people. So let's start out with a few definitions. Let's strictly define mathematically what a graph is. Let's first look at a simple graph, the graph below. Points A, B, and C are called the vertices of the graph. The lines between these points are called the edges of the graph. So the vertices of a graph are the objects being studied, whether a person, a town, etc. And the edges are the connections between the vertices, the relationships. So the edge E, AB, for example in our simple graph below, belongs to the graph, the connection between the vertices A and B. Since E belongs to the graph, then A and B are called the end vertices of E. We say that E is incident with A and B, and that A and B are adjacent since there's an edge connecting them. And this is a notation we use here to say A and B are adjacent. So now we are ready to define mathematically what a graph is. A graph consists of two sets: V, the set of all vertices of the graph, and E, the set of all edges of the graph, which are unordered pairs from V. And you see here E is a subset of the set of unordered pairs U1, U2, such that U1 and U2 belong to V. So now let's define the valency of a vertex. The valency of a vertex is the number of times it appears as an end vertex in the set E. In other words, the valency of a vertex is the number of edges that is connected to said vertex. In our simple graph, as you see, the valency of each vertex is 2, since two edges are connected to each vertex. So the edge set is this set here, E equals AB, AC, BC, and V equals ABC. Now let's go back to our street network. Here the vertices can be described as the intersections between the streets, and the edges are the streets themselves. Let's label each intersection as you see below. Let's give a few more definitions and then we're done with the definitions. A walk is a sequence of vertices, U1, U2, up to UN, such that for every I equal to or below 1 equal to or below n, we have UI adjacent to UI plus 1. So for example, in our street model, going from A to B to A again, then to E, is an example of a walk. A closed walk is a walk that begins and ends with the same vertex. A trail is a walk in which no edge is used more than once. A tour is a closed trail, a trail that begins and ends with the same vertex. An Euler trail is a trail in which every edge of the graph is used exactly once. An Euler tour is a closed Euler trail, an Euler trail that begins and ends with the same vertex. So basically the problem is asking us to find an Euler tour of this graph, which is a network of streets. There's a theorem in graph theory that says that a connected graph has an Euler tour if and only if every vertex in the graph has an even valency. So you might be asking what a connected graph is. I haven't defined this yet. A connected graph is a graph where if you take any two random vertices of this graph, then a walk U1, U2 exists between these two random vertices. So as you notice in our street network, all the vertices are of even valency. Some are 2, some are 4. So an Euler tour in this graph does indeed exist, my friends. So now we'll be using an algorithm that guarantees an Euler tour. Like I said before, you might have come up with a solution by brute force, but here we don't sacrifice rigor. So this algorithm is as follows. So we'll start the algorithm from Sarah's house, which is at the vertex H, since that's where the problem starts anyway. Vertex H is what we call the active vertex. Let L be the list of edges of this graph that haven't been used yet. Now choose any edge HX that is in L. Let C be a new sequence of vertices, starting with H. Put X at the end of the sequence C and make X the new active vertex. You repeat this process until there are no edges in L adjacent to the active vertex. So let's see how this is done by example. Let's start from H. So from H we go to G, then to F, then to L, then to M, then to N, then to E, then to L, then to H, then to K, then to J, then to I, then to H. And the process terminates because there are no edges left in L which are adjacent to the active vertex H. We've used them all up already. So now what do? We start the process again from the first vertex in C, that is an end vertex of an edge in L. So the remaining edges in L is as you see here. They haven't been used yet. AB, BJ, JC, CD, DE, and EA. So what is the first vertex in C that is an end vertex of one of the edges in L? It's E, right? That's the first one, since ED or DE is an edge in L. So we start the process again from E. So we go from E to A, to B, to J, to C, to D, to E. And the process terminates because there are no edges left in L. So we're done. So this second sequence, E, A, B, J, C, D, E, we put this in our original sequence C, where E originally was. So now we have the updated list sequence C, which is H, G, F, L, M, N, E, A, B, J, C, D, E, L, H, K, J, I, H. And that's your Euler tour right there. That's a path. And that's your answer. That's an Euler tour right there, my friends. So yeah, that was a pretty interesting puzzle, if you ask me. My first combinatorics puzzle, which will mostly be featuring graph theory, but not always. The field of combinatorics isn't just graph theory, it's other fields as well. So this was an easy combinatorics puzzle to get our feet wet, to familiarize ourselves with graph theory, since a lot of you might not be familiar with it. It's a pretty interesting field, my friends. More goodies on the way, guys. Algebra, logic, lateral thinking, geometry, probability, calculus, differential equations, set theory, chess, physics will be the main areas of focus on this channel. Smash those buttons like there's no tomorrow, my friends. And I'll see you guys in the next video. Bye-bye.